Hello and welcome to this lecture on trajectory planning. In the last lecture, we looked at dynamics, mainly Newton-Euler dynamics, where we saw how to find the equation of motion using Newton's equation and Euler's equation. Today, we'll move on to the next topic, which is trajectory planning. Now, what you have studied so far in your inverse kinematics is with reference to a point in space. So, given a position orientation of the end effector, what are the corresponding angles? But in order to move the end effector from one location to another, from one position to another position, we need to fit a trajectory onto the joint that will move it from one joint angle to the other joint angle. So, what should be the trajectory at the joint level? That is something what we'll be looking at today. So, today's topic is trajectory planning, and as we are slowly moving towards control systems, we will have to see that how do we plan the trajectory of the end effector, at the joint level, to take it from one position to another position. Now let's basically try to understand how a robot works. So a robot works something like this, that we have the joints. Let's consider revolute joints having 3 degrees of freedom, and we want to take it from there, from this position orientation to some other position orientation, which is here, for example. Okay, maybe just straight, we want to make it like that. Okay. So what the controller will do is essentially the controller, by doing inverse kinematics at location 1 and location 2. Okay, at location 1, it will find what are the corresponding theta. So theta 1, theta 2, theta 3. And so at location 1, it is theta 1, theta 2, and theta 3. Okay, and at location 2, it will do inverse kinematics and it will get the corresponding. For example, here it is theta 1 dashed, here it is theta 2 dashed, and here it is theta 3 dashed. So it will get theta 1 dashed, theta 2 dashed, and theta 3 dashed. Then it will do this minus this. It knows it has to go from, so joint number 1 has to go from theta 1 to theta 1 dashed. So the controller knows that. Okay, so what it will do is it needs to move the joint from theta 1 to theta 1 dash in some time t. Okay, so till now what we were doing in inverse kinematics, there was no time involved. Now we have to see that in the real world, we have to move the manipulator from one position orientation to the other position orientation. Now it can be done in 2 ways. What I mean is that I could fix a trajectory onto the end effector and say that it has to follow the trajectory like this. Okay, so from here to there, it's a trajectory basically. Let me color it with red. So if I'm planning at the end effector level, then I say the end effector goes like this. Okay, and I don't worry about the joint. But when I'm planning at the joint level, then I have to fit a trajectory onto the joint and say that the joint 1 has to move from theta 1 to theta 1 dash in some time t. Now, planning is done at the joint level. So trajectory planning, but before that, let's define what is a trajectory. So a trajectory is a time history of position orientation and trajectory is a time history of position, velocity, and acceleration of the joint, Okay, so till now when we were talking about kinematics, there was no time, but now there is time. So there is time history of, so this is the time history of theta dot, and theta double dot. Okay, and this is done at the joint level. Now, why at the joint level? Why not at the end effector level? That is essentially because if you are planning the trajectory in the end effector, say for example in xy coordinates, okay, so I can find the difference between x dash, y dash, and x and y, and then fit a spline onto that, or fit a curve onto that. Now, why do we not do it in the end effector level, but we do it in the joint level? Is essentially because of these problems, that if you are planning the end effector at the joint level, you'll be able to understand this very clearly. For example, we have a manipulator here. You can see that link lengths L1 and L2. L1 is greater than L2. So what would mean that there is a region in here where the manipulator cannot go. Okay, so this is a space, singular area where it cannot go. Now suppose I define a trajectory like this at the end effector level. It has to go from here to here. It is going through a singularity. It is going through a region in space where which is singular actually. So the robot actually end effector cannot go to that point. So this is basically showing that if you plan at the end effector level, at the end effector trajectory, okay, it may go and get into a singular position. It may go into a singularity. Now this would mean that you are only giving the start point and you're giving the end point. You're not interested in what is happening in between, right? And you cannot compute singularities, and you're not expected to know where a singularity is. So if you simply, in terms of planning, simply plan the path and say from this point to this point it has to go, it could be going in such a way that is going through a singularity, and this is going to be a problem. The second is, if we are having a manipulator which is like this, so it is going following a path, and on one side it is like this and the other side it is like that. Okay, so you can very well understand that there is some kind of inversion taking place here. Okay, so here also it is like this. Okay, so what you're seeing is that the manipulator on this position orientation, the manipulator is facing that side. On this position orientation, the manipulator is facing this side now. Okay, so these are inversion of one another. So inversions of each other, right? So this also is a problem, that suddenly there is an inversion which is taking place somewhere in the center, and this is not preferred. The second is again a similar kind of inversion. The third is some kind of inversion like this, where it is on one side, then here it is on this side. Again, there is an inversion problem. You can see that, right? So it is following in a straight line. So when it is coming exactly to this position where it has to switch sides now. Okay. So these are problems which are faced. Problems if you do trajectory planning. So if you plan the trajectory at the end effector level. Okay, trajectory at end effector level, at end effector. Okay. So to avoid this, what we do is we plan the trajectory in the at the joint level. So let's take the example of a very simple one-link manipulator. There's only one link. So this is one joint, theta1, and I want to go from this location to some other location. That is, I want to go to this location now. Okay. So that it will have a curve there because it is 1 degree of freedom only. So this is my joint position 1 and this is my position 2. Now, so theta1 is moved from this to this. Let's call it theta1 dashed. Okay. So now if I'm going to plan, if I'm going to fit a curve which will define how it is going from the first position to the desired position in terms of time, then what are the possibilities that are there? Or rather, in how many ways can it go there? If I were to plot, let's call this theta naught and let's call this theta f. Okay, so it is going from theta naught, a start point, to a final point which is theta f in time t. Okay, this is my time t, and so it is going from here, it is going through there. How many ways by which it can go there? So there are so many ways, right? Can it follow a straight line? Okay, can it follow a curve which is like this? Can it follow a curve which is like this? Okay, which one is it going to take? That is the question being asked. What is the trajectory that will take the single degree of freedom manipulator from theta naught to theta f in time t? Okay, so now what we see is, what about a straight line? Can a straight line follow this curve? Okay, what do you think? So if you look at the equation, suppose I write theta t is equal to a naught, okay, a naught plus a1t. Okay, that's a straight line. Okay, do you think it's possible for the manipulator to follow this at the joint level? Okay, now if you think a little bit, it will become clear that it cannot. Why? Because if I take the derivative of this is equal to a naught, so a naught is going to become 0, so it will become a1. So which means the velocity is constant. Okay, now again if I take the second derivative of this, theta double dot t, it will become 0. It means there is no acceleration. Okay, so a body cannot move from one location to another location with a constant velocity and if the acceleration is 0. It's not possible in the real world. So if that is not possible, then we need to fit a curve where the motion is possible. Now, what is the type of motion that we are targeting? we want. First of all, at time is equal to 0, it is here. At time is equal to tf, it is there. So these are two constraints. Okay, at time is equal to 0, it should be at theta naught. At time is equal to tf, it should be at theta f. Okay, anything else? The other thing we need to, the other constraints are at time is equal to 0. Okay, the velocity should be equal to 0. Theta naught, theta dot should be equal to 0. Okay, because otherwise what will happen is it is not at rest. The body is starting from rest, right? So at time is equal to 0, theta naught is equal to 0, means velocity is equal to 0. And at time is equal to tf, theta naught is equal to 0 again. So it has to come to rest. So the way of writing it is theta naught is in tf is equal to 0. Okay, and at time is equal to 0, so theta naught of 0 is equal to 0. So there are four constraints. The first constraint is at time is equal to 0, it is at location theta naught. At time is equal to tf, it is at location theta f. At time is equal to 0, the velocity is 0, so that's my third constraint. And at time is equal to tf, the velocity is again equal to 0. That's my fourth constraint. So these are the four constraints that are there in this robot. Okay, so you can imagine that when it is starting, it is at rest. When it is ending to location 2, it is again at rest. Okay, and starting is theta naught and ending is theta f. So there are four constraints. Now let's look at the constraints. So the constraints are at theta is equal to time is equal to 0, the location is theta naught, and at theta equal to tf, okay, it is equal to theta f. So there are two constraints here. What are the other two constraints? The other two constraints are at velocity constraints. At time is equal to 0, this is equal to 0, and theta naught at tf is equal to 0. Okay, time is going from 0 to tf. Okay, so now what we can do is, because there are four constraints, these four constraints can be satisfied by a polynomial of at least a third degree. Okay, a straight line is not possible, we have seen. Now if you put a cubic, you put a parabola erased, then also you'll find it is not possible. That means equation of order 2. Okay, then also you'll find that it is not possible because your acceleration will become constant then. Okay, so we are going to write, this is represented by a cubic polynomial of order of degree 3 at least, which is equal to a naught plus a1t plus a2t t squared plus a3t cubed. So there are four constraints and we have four coefficients here, a naught, a1, a2 and a3. Now how do we solve? Now let us find the derivative of this. The velocity is equal to a1 plus twice a2t plus thrice a3 t squared. What about theta double dot t, which is equal to, if I differentiate with respect to t, what I get is 2a2 plus 6a3t. Okay, so we have seen velocity and we are seeing acceleration. So now what I do is, I say, let me call this equation 1, this is equation 2, and this is equation 3. So I take my constraints. So these are my constraints. Okay, so I take my constraints and I put them, the position constraints, I put them in equation 1, so I get two equations. Okay, so at time is equal to 0, all time will become 0 here. So theta naught will become equal to a naught. Okay, why? Because all the others are going to become 0. Time is 0. Now at time is equal to tf, it is equal to theta f. So theta f is equal to a naught plus a1t, a1tf plus, this is a2tf squared, okay, plus a3 tf cubed. So I took the second constraint and I put it in equation 1, and this is what I get. Okay, t has been replaced by tf. That's all. Now so these are the position. Now what about the velocity? So I take equation number 2. So I take constraint on the velocity and I put it in equation number 2, and what we get is velocity is equal to 0 at time is equal to 0, so a1 is equal to 0, and then velocity is equal to 0 again when time is equal to tf. So what we are going to get, again another equation, 0 is equal to a1 plus twice a2 tf plus thrice a3 tf squared. That is from equation number 2. So we have got the solution for this. We have got a0 equal to theta naught and a1 equal to 0. Okay, 2 we have got. So we have 2 more left. So a2 is left and a3 is left. Now there are 2 equations here, equation 4 and equation 5. So I can 2 equations, 2 unknowns, we can solve and we can get the required solutions, right? So the required solutions are, the first one was a0 is equal to theta naught and a1 is equal to 0. Then solving those equations 5 and 6, we get a2 is equal to 3 by tf squared divided by theta f minus theta naught. Okay, and a3 is equal to 2 by tf cubed into theta f minus theta naught. Okay, so now we have got for a0, a1, a2, a3. So we have all the parameters of the cubic polynomial that we proposed. Okay, so this is my cubic polynomial. Okay, we have got a0, a1, a2, a3. Okay, so for a manipulator joint to move from theta naught to theta f in time tf, we can find the coefficients a0, a1, a2, a3 and put them in this equation and get its get the equation of motion. Okay, not equation of motion, the trajectory of the joint, and then we can plot. So how do we plot? What we can do is we can put small increments of time, say 0.1, 0.2, 0.3, and then see how the position, velocity, acceleration is changing. Okay, so let's do that. Let's do a very simple example to understand this better. So what we are saying is we are trying to fit a trajectory onto the joint of the manipulator, which is going to take it from one position to another position, and we are fitting a cubic polynomial onto the joint. So if there are 3 joints, so we have theta 1, theta 2, and theta 3, there are 3 joints. So we'll have 3. Now we'll have 3 cubic polynomials. Okay, 1 for each joint, and that is what the controller actually will be controlling. So let's move on and look at a very simple example to understand this better. Okay, so let's look at an example. So my example is here. It is let's say we have a single link robot is stationary at theta is equal to 15 degrees. Okay, and it has to move to theta equal to 75 degrees. Okay, in let's say 3 seconds. So 75 degrees in 3 seconds. Okay, so let me draw it here. So at 15 degrees it is here. Okay, at time is equal to 0, it is there. Now at time is equal to 3 seconds, when time is equal to 3 seconds, it is at 75 degrees. So this is 15 degrees and that is 75 degrees. So this is the question. Okay, the question is fit a cubic polynomial and find theta, theta dot, and theta double dot as function of time. Okay, it means plot as it is moving. We also want to see the variation of theta, theta dot, and theta double dot. That is the meaning of this. So we are given theta. What we require is theta, theta dot, and theta double dot. So let us first note down what is the cubic polynomial. So theta t is equal to a0 plus a1t plus a2t squared plus a3t cubed. Okay, this is a cubic polynomial. Now, so there are 4 coefficients, and we have 4 parameters, and we have 4 constraints. So what are the 4 constraints? The 4 constraints is at time is equal to 0, theta of t, at time is equal, equal to 0, this is equal to 15 degrees. Start at time is equal to 3 seconds. This is at 75 degrees, it is given. What are the other two constraints? Theta naught at 0 is equal to 0, and theta naught at 3 is also equal to 0. Okay, now we have found the expressions for a naught, a1, a2, and a3. We know what is theta f and what is theta naught. It is given here. One is 15 and one is 75. We know time, tf, time is equal to 3 seconds. So all I need to do is to put it into this equation. This, and this. A2 is 0, a1 is 0, so it doesn't matter. Okay, so all I need to do is put in the values, and I'll get the expression, and what I'll get the values of the parameters. Okay, so putting in, so let me write it here as putting in equations. Let's call this equations, the previous one was 5, so let's call this 6, putting in equation 6. Okay, so putting in equation 6 equation, we get, what we do get is a naught is equal to 15. Okay, then a1 is equal to 0, a2 is equal to 20, and a3 is equal to minus 4.44. We just have to put the values in the numerical values, and you'll get this. Okay, now, so what is the equation of the cubic polynomial? The equation of the cubic polynomial is given by theta t. Theta t is equal to 15 plus 20t squared minus 4.44 t cubed. Okay, so a1 is 0, so a1 is not here. Okay, now I'm asked to find the position, velocity, and acceleration. So for position, I take the derivative, and what we get is 40t. I just differentiate this, and I get 40t minus 13.33 t squared, and theta double dot t is equal to 40 minus 26.66 t. Okay, so we have position, we have velocity, we have acceleration. Okay, now we need to plot and see the variation of velocity, position, and acceleration. Okay, now let us plot. How do we plot? We have the equation, this equation for position, this for velocity, this for acceleration. So I start with t is equal to 0. Okay, let me plot here. So I start with t is equal to 0 and increment t by small amounts of maybe 0.1, 0.1, 0.1 like that. Okay, till 3 seconds. So this is 1 second, 2 seconds. So increments of 0.1, I just put it into that equation, and whatever is my theta. So I start from 15 degrees, and at the end it is 75 degrees. Okay, so it has to go, okay, there. So basically I put the values of 0.1, 0.2, 0.3 t like that, and see what is the variation of theta. So this is my theta variation. Now what will be the curve looking like? The curve will look something like this. Sorry, this is not right. Okay, curve will look something like that. Okay, so that is my theta axis. This is my time axis. Okay, now let us look at the variation of velocity. So I take equation number 2, this equation, and I put small increments of time, say 0.1, 0.2, and then see how does theta naught vary. Okay, so the variation of theta naught, if you look at the equation, this is a plus, but there is a minus here. So it basically means that acceleration is going to increase, and then it's going to decrease, because there's a plus and a minus there now. So what is the maximum value? The maximum value will be 26 point something. What will be the maximum value? The maximum value will be somewhere here. So halfway value, so this is my 3. So exactly halfway, what will happen is the velocity will go up and then it will come down. Okay, exactly half. Okay, because of acceleration and deceleration, so this fellow will exactly be here now. Okay, so this is my variation of velocity with respect to time. This is just below 30. Okay, now So what is the value? This value you're going to at exactly 1.5 seconds. Okay, exactly at 1.5 seconds you'll get the value of theta here now. So put it in this equation and you'll get what is because at that point the velocity becomes 0. Sorry, the velocity doesn't become 0, but it changes direction. So plus it becomes minus. So what about the variation of acceleration? So this is my, let's do acceleration this side. So this is my acceleration, position, velocity, and acceleration. So this means it is an increasing velocity and there is a decreasing velocity. Okay, this one shows an increase and decrease, and where it is going to switch over is going to be exactly at 1.5 seconds. Now, what about acceleration? Now, acceleration, again, it will start with a high acceleration. This is my time axis, and that is my theta double dot axis. So what we'll see is that it is going to go like this and like that. Okay. Now, this is showing that if you look at this equation, okay, what is the acceleration at time is equal to 0? At time is equal to 0, acceleration is 40. Okay, from this equation. So it is there, and at the end, and in 3 seconds also, it will come back here. So this is my time, and exactly at 1.5 it will cross the middle section. So from the positive side, it will go to the negative side. So this is the variation of theta, theta dot, and theta double dot. Now, now the question that's important here and interesting here is this possible? Okay, we have, this is a real robot, this is a real single link which is rotating, and we are saying that this, we are fitting a cubic polynomial and we want to move it from rest to rest in some time tf. And if we do that, then when we plot the position, velocity, and acceleration, then it comes out like this. This is the variation of position, the one on the extreme left. This is velocity, and that's acceleration. First, let's understand. The velocity increases and then decreases. Maximum velocity is reached at half when time is equal to 1.5, okay, or t by 2 here. If you put the value into this equation, you'll get the maximum velocity. What about acceleration? In terms of acceleration, what we see is that because there is no t here on this term, when time is equal to 0, the acceleration is 40. Okay, so this is possible. Okay, this is also possible. Okay, but what about acceleration? So it is showing that when time is equal to 0, theta double dot is equal to 40. Okay, which means that the system is instantly going to that acceleration at time is equal to 0, which is not possible. Again, where time is equal to 3, you see it is here. Okay, so again, there is instantaneous change of acceleration, which is not possible for a real system. When time is equal to 0, acceleration can't be 40. So this is not possible. Okay, so if this is not possible, then what we can do is there is some kind of discontinuity at time is equal to 0 and time is equal to 3. This is what is happening. So what we can do is we can try and modify this cubic polynomial in such a way that the robot starts very slowly, okay, and then it has a linear section, and then it comes to rest very slowly again. So what that is called the linear function. So linear function with parabolic blends. Okay, so what this is basically saying is that a part of it is going to be linear, a part of it is going to be parabolic. So let's look at it this way. So we're going to start from here, theta naught, and this is my final theta f, where we have to reach in time tf. So let's say this is my time tf now. Okay, and time is equal to 0 from here. Now what we are going to do is we are going to divide this into regions and say that from here to here it will go very slowly like this. It has parabolic. Then from here to here it is going to become linear, and then it will become parabolic again. Okay, so what we are saying is that it has a linear function with a parabolic blend. So this part is linear, means constant velocity, and then there is a parabolic blend at the other end, which is going to okay, this should be the same. It should be the same. So the two linear, the two parabolic sections are the same. Okay. So I hope you understand this, that the parabolic sections are the same. Okay, so it is somewhere here. So now the robot is starting with a parabolic blend. So this part is what we call the parabolic blend. Okay, parabolic blends. Now, something to note here is that the time of the parabolic blend is TB. Okay, and exactly on the center portion, this is TH, T halfway. Okay, it is symmetric about the halfway mark. Now, in terms of the thetas, this is theta H, halfway mark, and this is theta B, where is the distance it has moved in the blend section. So with this now, we want to find out what will be the equation, or how to perform this kind of motion. Okay, so we want to go from theta naught to theta B in a parabolic way. So theta naught to theta B is parabolic. Then from theta B to the top of it, let's call this theta B dashed, that part is theta B dashed, to theta B dashed, it is linear. Then again from theta B dashed to theta F, it is parabolic. So it basically means that it starts slowly and stops slowly. Unlike the previous case, if you remember the previous case, here there was an instant start and there was an instant stop because of the acceleration. Whereas here what we are saying is that it will start slowly in a parabolic way and it will stop slowly. Okay. Now, because this is a linear section here, in the center it's linear, so the velocity is constant. Okay. Now, the other assumptions that we are making is that in the parabolic section, the acceleration is constant. Parabolic section, acceleration is constant. Okay, and the other assumption is that the velocity at end of blend, okay, that means at TB is equal to velocity at start of linear section. Velocity at start of linear section. Okay, so this is the assumption that we are making. And now when we see if we use our equation, okay, then what we see is that the velocity at the end of the blend section must be equal to velocity of the linear section. So we have so from this equation, v is equal to u plus at. Okay, for the blend section. Okay, we have what is u? U is the initial starting velocity, which is equal to 0, initial velocity. What is the final velocity? Final velocity after the blend is equal to the velocity of the linear section, right? So at, this is my acceleration. Suppose I say this is equal to theta double dot. Okay, theta double dot, okay, is the acceleration at the blend section. Then using this equation, what we get is at theta double dot into TB, T of blend, that is TB. Okay. Okay, that is one equation. The other equation, sorry, we are not using this equation. We are using the other equation. S is equal to ut plus half at squared. We are using that equation. Okay. So what we are saying here is that the distance covered is equal to S, which is equal to, this is equal to theta B minus theta naught is the distance covered. U is equal to 0. Okay, the initial velocity is equal to 0. So we have half at squared, half a is equal to theta double dot TB squared, okay, is equal to S, the distance, which is theta B minus theta naught. Okay, So the equation I have used is essentially s is equal to ut plus half at squared. So from physics we know that, right? So the equation we are using is s is equal to ut, distance moved, is equal to ut plus half a t squared for the blend portion. So in the blend, the s distance moved is equal to theta b minus theta naught, and we are making the acceleration equal to theta double dot. That's an assumption, and t is equal to tb, the blend section. So from that, what we are getting is u is equal to 0. So what we are getting is half a t squared is equal to theta b minus theta naught. This one equation. So this is equation number 1. Okay. Now this is one equation considering the kind of motion in the parabolic section. The second equation that we are getting is in terms of the velocity. Okay. In terms of velocity, v is equal to u plus at. Okay. So the velocity, again, initial velocity is 0. So the velocity at the end of blend is equal to the start of the linear section. Okay. And what is the average velocity? Average velocity is equal to theta h minus theta b divided by th minus tb. Let me go back and look at this again. So the velocity at this point here is equal to theta h minus theta b divided by th minus tb, the average velocity, right? So that's the velocity at this point. Okay, so it is this distance, theta h minus theta b divided by th minus tb, and this velocity must be equal to the velocity that is coming from the blend section. Both the velocities has to be equal. What is the velocity coming from the blend section? That is equal to v is equal to u plus at. So starting velocity is 0. It has acceleration theta. Acceleration is equal to theta double dot, we saw, and t is equal to tb. Okay, so acceleration is theta double dot, and what is time? T is equal to tb. Right. Now from this, what we get is, from this equation, u is 0. So v is equal to theta h minus theta b divided by th minus tb is equal to at. What is a? It is equal to theta double dot into tb. Okay. So this we are getting from this equation. So we have two equations now. Equation, what was that equation number? Equation number 1, and this is my equation number 2. Okay, so this is my, let's call it equation number 2 now. Now a couple of things, other things that we are seeing is that the th, that is the section of the blend, is exactly equal to, is halfway. Therefore capital T is equal to 2th. Okay, so so this is my equation number 3, let's say. So combining equations 1, 2 and 3, we get this equation, that theta double dot into tb squared minus theta double dot t into tb plus theta f minus theta naught is equal to 0. Okay. Now what we see is that what is known and unknown here. Known is theta naught is known, start point, theta f final point is known. Okay. Now t total time tf is known, total time t is known. Okay. So this is also known. So what is not known is tb. So tb is the fellow who is not known. Okay. So what this means is that tb can be db can be moved on the right side, or it can be moved on the left side. Okay. So, and that depends on the acceleration that you're choosing, right? So in this equation there are two unknowns. tb is one unknown and theta double dot is the other unknown, the acceleration in the blend period. That itself is not known. Okay. So for different theta double dots, you'll get different tb's. So if it is accelerating very fast, okay, then your tb will move towards this side. Now if it is starting very slowly, accelerating very slowly, your tb will move on the right side. Okay. So it depends on the acceleration you are choosing now. So what it basically means is that there is a bound on tb now. Okay. So in this equation, it is tb squared minus so and so. So if you find the value of tb, this is a second order equation. So if I find the root, tb is equal to half t by 2 minus root over p squared minus 4mk, that is theta double dot squared, into t squared minus 4 theta double dot into theta f minus theta naught, okay, divided by 2 theta double dot. Okay, so one of the roots of this equation is here. This is of the form, this is a second order equation, so I can find the the roots this way. But now what we do see is that this term here is coming under the square root. Okay, so what we see is that this term here is coming under the square root sign now, which means that there is a bound. Why? Because TB, what is TB? TB is time. Okay, time cannot become imaginary. It cannot become imaginary, nor can it become negative. Okay, both of these are not possible. So this basically means that there is a constraint on your acceleration now. And the constraint on the acceleration is that theta double dot, the term which is coming inside the square root, theta double dot squared into t squared minus 4 theta double dot into theta f minus theta naught by 2 must be greater than 0. Okay, greater than equal 0. Now this tells us that theta double dot must be greater than 4. Theta double dot must be greater than 4 theta f minus theta naught divided by t squared. Okay, else what will happen is this fellow will become 0. Okay, so this condition is a condition that is required. So when you are choosing your acceleration for the, while choosing acceleration theta double dot during blend period, this is a constraint. Okay, so this constraint is something that we have to keep in mind when we are choosing theta double dot. Now, when equality occurs, what is going to happen? That means when equality occurs in this equation, okay, so theta double dot is greater than equal to this. So if it becomes equal to this, what will happen? It basically means that your blend portion has gone so far that it has gone here now, okay, and the other blend portion has come from here to here. You don't have a linear part now. Okay, that is the meaning of your equality. Now it can't be less than, because if it becomes less than, then time will become imaginary. Now you cannot have imaginary time. Okay, so basically what are we choosing here is we have to choose the value of acceleration such that we get a desired TV. If it's not too small, it's not too large. Okay, now let us look at an example here, and the same manipulator that we were talking about just some time back. It is 15 degrees. It is moving one single link manipulator, moving from 15 degrees to 75 degrees. So 15 degrees to 75 degrees in 3 seconds. Okay, this was the problem we were looking at some time back. But now what we are saying is we are going to use linear section with, so linear section with parabolic planes. Okay, now so what we need to choose is theta double dot. So we can choose a high value or we can choose a low value. Depending on what values we choose, there will be variation in theta, theta dot and theta double dot. Okay, so basically this is to show that depending on the value of theta double dot, you'll get different. So let us, for low values and high values of acceleration, what do we get? Okay, so first of all, let's take a case of a high value of acceleration. Okay, so let us take the example number 1 is theta double dot has a high value of acceleration. Okay, acceleration is high. So what we do get is variation like this. This is my position. Okay, position is 0 to 3, and this is from 15 degrees to 75 degrees. So what we do get is a variation like this, straight line and then up. Okay, in the middle it is, so that's 3. In the middle it is linear. So there is parabolic, and then a linear section. Okay, now correspondingly, if I draw, okay, so I'm correspondingly drawing. This is theta, this is theta dot, okay, this is time. What will the velocity look like? So in the blend period, the velocity will go up like this, then it will remain constant, and then it will come down, and then come down like that. Okay, and both sides will be equal. Okay, please note that both the sides are equal actually. Okay, so this is showing that in the linear section, the velocity is a constant velocity. Okay, now what about acceleration? So if you look at acceleration, what we do find is accelerations, we said it's a high acceleration, so it starts like this. These points are all corresponding. Okay, goes high acceleration, remains constant, or zero acceleration. Constant velocity means zero acceleration, and then it comes down like that and goes in here. Okay, so if you compare the graphs, these three, position, velocity, and acceleration, with that of the previous position, velocity, acceleration that was here. Okay, let's look at the previous graph. What was the graph here? Yes. So you look at the acceleration here. Okay, look at the velocity and look at the profile of the position. Okay, whereas you see the corresponding change here, that there are two blend portions and there's a linear section. So the linear section is marked in red. So it is a linear section here. So this is fully linear. Okay, that is one. The velocity is constant here, and the acceleration is there. Acceleration is 0 in the central portion, and then comes down. Okay, so we are starting with a smaller acceleration and then going there. Now, if acceleration is slightly lower, so theta double dot is low, then what will we get? Let's draw all three of them and see. What happens is theta dot is equal to 15 degrees to 75 degrees. Okay, time is equal to 3 seconds again. T is equal to 3 seconds. What is the variation of position? So we'll see that what basically happens is when acceleration is lower, okay, this is velocity, position, and acceleration. So this is theta dot, and theta double dot. Okay, so basically what we are seeing is that what happens is that the time of blend has gone up now. Your time of blend has gone up like this, then it becomes straight line, it comes down like this. Okay, so correspondingly velocity graph, the velocity has gone up like this, it has remained constant and come down like this. Okay, this region has become smaller. Okay, and what about the accelerations? The accelerations we find is acceleration is somewhere here. It's a low acceleration, so it was like this, like this, like this, like this, and this. So the meaning of low acceleration is that it will take more time for the acceleration to reach the for the link to reach the end of blend. Whereas if it is having higher acceleration, then it will reach the end of blend much faster. Okay, so this basically shows the effect of high and low acceleration, and this is a practical way of controlling the robot link. Okay, now the other challenge that is there is that although we are saying the acceleration can be high or low, unlike in the previous case, even here at time is equal to 0, it has an acceleration. So what we can do is we can make it rise slowly like this. Okay, it will rise slowly and it can fall slowly. Okay, then it becomes more realistic. Why? Because a electrical motor will take some time to accelerate. Okay, that is your time, the motor time constant, and depending on that we can choose the acceleration and then proceed with the blend section. Okay, so this is a practical way of fixing trajectories, okay, or trajectory planning of a manipulator which is going from one link to the other, which is going from one position to another position. Now we have said that one of the constraints that we have put is that the manipulator joint moves from one position to another position. This is a link, and we have another one here like that. We said that it is going from one location, one angle to another location, theta naught to theta f in some time tf. Okay, but by doing this we have no control. So there will be one trajectory which will be fitted for this joint, there will be another trajectory fitted for this joint, cubic polynomials. But by doing that we have no control over the end effector, what the end effector will do. Okay, so because there is a Jacobian, you know, so x dot is equal to j into theta dot. and there are sine cos terms in here. So it is difficult to predict what that end effector is going to do. Okay, so it could do like this, it could go like this, it could go like this, it could do something else. Now suppose we also want to control the end effector trajectory, then what we can do is we can put one wire point. So this is a wire point. Okay, so I say start point, this is goal point, and this is my wire point. Now let me explain it like this. This is goal, this is via, and this is sorry, the other way around. So what we can say is we can say start point is here. Okay, start, via, and goal. What we said in the previous case is the start and the goal remains having the constraint that the manipulator is at rest. Okay, so here theta naught at 0 is equal to theta naught, and theta naught 0 theta dot, sorry, 0 at is equal to 0. That's start point. That remains. But at the via point, what we can do is we are fixing one polynomial like this, another polynomial like this. Okay, so what we can do is the end velocity here will become equal to start of the next one. So end of 1 will become start of 2. End of 1 will become start of 2. It won't be like this, but it should be continuous. Okay, so this is my via point. So in order to maintain that continuity, what we'll say, the end velocity of the first cubic polynomial is equal to the start velocity of the second fellow. Okay, so what we are saying here is, if we say this is tv, okay, time of blend of via point, then theta dot, so the end velocity of polynomial 1, okay, is going to become the start velocity of the other guy. So the start velocity of the second polynomial, okay, so theta naught tv will become equal to theta dot f, and theta dot f will become equal to the start velocity of the second one. Okay, so this will become start of second spline, cubic spline. Okay, so I hope it is clear that we have two splines now, or two cubic polynomials. The only difference being that they are at rest here. They are at rest here. Start point, goal point we know, but at the via points, what will happen? The end velocity of this will become the start velocity of this fellow. Okay, so we have two cubic splines for four conditions, and we solve the problem exactly the same way we solved it. So what we get is at the via points we have to put velocity constraints, and the start of the second spline will have the velocity of the first spline, and then we can proceed to solve it exactly the same way. Okay, now so this basically means that you have something in your hand now, and what we have in our hand is, number one, the user specifies the desired velocity at each via point. So the user specified desired velocity at via points. Okay, and that is one way the user is specifying. Now they could be automatically found, automatically obtained, for example, by applying some heuristic in either Cartesian space or joint space. Okay, for example, it must there is some threshold on the velocity, and it must choose a velocity within that velocity. That is automatically chosen based on some heuristic. Okay, now the third is the system automatically chooses the velocity at via points. Velocity chosen to maintain constant acceleration. Acceleration at via point. Okay, So at the y point, to maintain this acceleration constant, it will choose the velocity in such a way. Now this is trajectory planning using via points, and it's very easy to understand that the same logic is used for two trajectories now. The only difference that they are being connected in the center by a via point, and the velocity of the first one, end velocity of the first one, is equal to the start velocity of the second one. But if you do that, then what happens? There is no automatic way by which the velocity gets fixed. In that case, what we need to do is we need to specify the velocity by the user, or satisfy the constraint that at that via point the acceleration will be same. Okay, for same, I mean the accelerations will be continuous. Okay, for the switchover which is taking place at the via point. So with this, we have discussed about via points and trajectory planning using cubic polynomials. Now in the next class, we'll be moving on to more towards the control systems part. So we'll be talking about sensors and actuators. How does a robot actually move? So far we have been doing kinematics, which is the mathematics. Then we did dynamics. Then we did trajectory planning. Now we understand that the use of inverse kinematics, and also from inverse kinematics we get the start point, end point. Now we have to fit a trajectory, and the trajectory has to be enforced by the controller now. Okay. So from the following class, we'll move on to sensors, actuators, and then we'll move on to robot programming. So now we'll look at via points. So in what we have done so far is we have a start point and we have an end point, and we are going from the start point to the end point using one cubic polynomial. Now suppose we want to go from a via point by using to ensure that the end effector follows the trajectory that we want it to follow. So what we'll be doing is we have let's say theta 1 is going from theta naught, and it is going to another point. Now let me draw it like this. So we have one point here which is theta naught. From here it is going to another point which is let's call it theta 1. Then from here it is going to another point which is theta 2, and then it is going to another point which is my theta f now. So what we are saying is that it is going via this point and via this point. Okay, initially we were saying it was one polynomial which was going from here to here. Like now we are saying it is going from here to here, then from here to here. Now what is the basic difference? The basic difference is that all three of them are cubic polynomials now. So this is also a cubic, this is also a cubic, and this is also a cubic. All are cubic polynomials. Now the difference being that in here the start point, the velocity is theta dot is equal to 0 here, and it is also equal to 0 there. Theta dot is equal to 0 at the final point. But this point and this point, the velocities are not 0. Okay, in order to maintain continuity. So what we are going to do is we are going to say that so if you're just going to make a cubic for this part, cubic for this section. Okay, now the velocities are not constant, so we can say that at time theta is equal to 0, the position is theta 1. Okay, and velocity at velocity at the section is equal to let's call it theta naught dot. Okay, well, this is not theta naught dot, so let's call it theta 1 dot. Let's call it theta 1 dot. Okay, now this is 1. Now in this position here, the final of this one again is theta at time, whatever is the time t, will be equal to the position which is let's call it theta 2. Okay, and what will be the velocity at so theta dot at time t of let's call it the end of blend point, sorry, not blend point, via point, will be equal to theta dot f. Okay, that means in the previous case these two velocities were 0. In this case we are saying that these two velocities are not 0, but they are having a particular value. Okay, so if you do that, then what we get is 4 equations now. Our 4 equations will be in terms of the velocities, okay, and in terms of the positions. So what we can do is we can simply put this this and this in our equation, that is theta t is equal to a0 plus a1t plus a2t squared plus a3t cubed, the same thing, okay, and write it and solve it for this and this now, okay. So what we have seen is that this is exactly the same cubic polynomial, but the only difference being that the velocities are not zero at the start point and the end point of this cubic polynomial. Positions are whatever is the position that is desired at the y point, that is there, but the velocities are not zero. Now by doing this you can solve it again exactly in the same way, and you can get you can solve for a0, a1, a2 and a3, okay. So what we have seen today is trajectory planning for a manipulator which is going from start to end without a wire point and also with a wire point. Now when we have this wire point, what we can do is you need to choose the velocity of the wire point, okay. So what is going to be this velocity and what is going to be that velocity, okay. So now we can choose the velocity in this way. So in order to choose the velocity, there are 3 ways of choosing. Number 1, it is user specified. So the user specified what should be the velocity at the wire point. The second is there is some automatic algorithm. We can call it automatic heuristic maybe, or some suitable heuristic that is going to find out what is the velocity, to compute the velocity. Okay, and the third could be that we can automatically set the velocities at the wire point such that the accelerations will be continuous, so that the velocities are set for continuous acceleration at wire points, okay. So with this we come to the end of the lecture for today, trajectory planning, and we are now moving towards the area of control systems, okay. So we finished automatic we finished our trajectory planning today, and then we'll slowly move towards control systems, where we'll look at how the trajectory is actually enforced by the controller. So we stop today. Thank you.